back to our course on memory device technology for AI/ML computing. So the last time around we were studying about the read operation of an SRAM cell, and we concluded the read operation by looking specifically at the read timing diagram. Very quick recap of how a read happens and how do we monitor the read operation with respect to time. As you know, we were dealing with the case where storage node 1 had a value of 0 and storage node had a value of 1. So the first thing that we do is pre-charge the bit line and bit line bar to VDD, and the word line is enabled. When the word line is enabled, it so happens that the read current starts flowing from the left hand side of the branch, in the branch where the value 0 is stored, and there is a read current which flows from PG1 to PD1. Because there is a small read current which flows from PG1 to PD1, definitely storage node N1 cannot stay at 0 volts because there has to be a potential drop for any current to flow. So this results in a slight increase, as you can see from the timing diagram. When word line was asserted, there was a slight increase delta V in the voltage at storage node V1 or VN1. However, through appropriate cell ratio design, we managed to see that this noise margin is well, or this change in delta V is well within the noise margin, and therefore you are able to facilitate a non-destructive read. And because you had the ability to stabilize VN1 and VN2, recall how that happens. The stability of VN1 and VN2 comes from this positive regenerative feedback of this cross-coupled inverter, which is at the heart of the SRAM cell. We looked at this very carefully, and at the end I asked you a couple of questions. The first question that I asked you was, since VN1 voltage is changing and the output of VN1 is connected to the input of the second inverter, the right hand side inverter, definitely there will be some change in VN2 also, and that is also indicated in the timing diagrams. So if VN2 is slightly moving away from 1 volt, so it is becoming 1 minus delta V dash volts. As you see, there is a small drop in the voltage at VN2. Does our original static analysis, where we assume that PG2 is turned off, is still valid? And some of you might have already thought about it and realized that that is not really the case. What will happen essentially is, when N2 becomes slightly smaller than 1 volt, 1 minus delta V, there is a significant chance that PG2 transistor may turn on, because under the condition that this delta V, now this delta V, 1 minus delta V, forms the difference between the VGS, between the gate voltage and the source voltage for the PG2 transistor. And if this delta V is greater than VTH, then there is a significant chance that even the pass gate transistor will turn on. And if the pass gate transistor does turn on, there could be, for a very small momentary time, some leakage current which can flow through this PG2 transistor. But as you can see, that will be very quickly stabilized by this VDD supply voltage through this pull-up transistor. So VDD supply voltage will try to stabilize VN2 in the case that there is a small current that flows through a transitory time through this VN2. Nonetheless, another important design constraint that you try to manage is the cell ratio. As we know, this delta V, which is the voltage that changes in storage node 1, is controlled completely by the cell ratio of the transistor, and making sure that the cell ratio is very large, or in this case the pull down transistor is significantly stronger than the pass gate transistor, you can avoid this issue, and ultimately you can make sure that VN2 does not for a significant period of time increase, or the change in VN2 does not significantly alter the operation of this pass gate transistor, which is to be off. Okay, so this is the answer to the question that I had asked the last time, and now we will move on to another very important operation, the second most important operation in SRAMs, and that is the write operation. So we did a detailed analysis of how read operation happens. We did a static analysis which enabled us to understand what is the cell ratio, and also we did a timing analysis. Now we will go ahead and look at the write operation. Now, what are we trying to do in the write operation of an SRAM cell? Remember, I was always encouraging you guys to analyze the SRAM cell in the form of a double potential well, or a W-shaped potential well. So in the W-shaped potential well, read operation involves not disturbing. For example, in this case you can see that this double potential well is in one stable state, which I am indicating with the laser pointer. In read operation, you didn't want to disturb this double potential well, and you wanted to read what is the state at which this SRAM cell is in. However, in the write operation, you want to do exactly the opposite. You want to ensure that the SRAM cell, which is in one stable configuration, either in 1 or 0, is flipped to the other stable configuration. And as you can understand, there could be two very interesting and independent approaches to do write in the SRAM cell with positive regenerative feedback. Okay, so the entire point of trying to do write operation is, please remember, the SRAM cell has this memory effect because of this positive regenerative feedback. You are trying to circumvent it or overcome this positive regenerative feedback and be able to flip the position from state 1 to 0 or to 0 to 1. Equivalently, in this W-shaped potential barrier, what you are trying to do is, suppose you are in this stable configuration, somehow you want to supply enough energy to one configuration so that it can overcome this barrier and jump over and enter the other stable configuration. Now, as it turns out, as I just mentioned, there are two independent approaches to do that. Let's look at them in some detail. The first approach, as I just mentioned, is completely overpowering the positive feedback to make sure that point A and B, the metastable points that we saw, A and B, the stable points get transferred into metastable points, and therefore if we give it enough energy, the state will be able to flip. And how is this facilitated? This is facilitated in the SRAM cell in the following manner. So I have represented this with a diagram. So you have your cross-coupled inverters, as you can see that I am indicating. Before you are doing the write operation, we will assume that N1 has a value of 0 and N2 has a value of 1. And our objective is to flip the value of N1 from 0 to 1. So before it was 0, next it is 1. And how do you do this? Again, you take the help of the pass gate transistor. So what you do is, of course, you will have to enable the pass gate transistor, and you have to write a very strong VDD or a strong 1 on one end of the pass gate transistor. So on the drain end of the pass gate transistor, as I am indicating, you have to write a strong 1, and you have to ensure that this pass gate transistor is enabled. So this strong 1 can somehow overpower, somehow overpower the value which is already written in N1. Okay. How do you overpower? It is very simple. You overpower by making sure that this pass gate transistor or the MOSFET, the N MOSFET has much higher drive strength. The pass gate transistor has much higher drive strength or low on resistance compared to the heart of the circuitry, which is your cross-couple inverter. That is the first thing that common sense suggests. The other thing that you have to ensure is that this enable signal or the overpowering enable signal has to be maintained or has to be enabled for a minimum of 2 times the delay of your cross-coupled inverter. So a single tau delay, as you know, a CMOS inverter has an intrinsic delay. 2 cross-coupled inverters will have a intrinsic delay of 2 into tau delay. So it makes sense that this trigger pulse where you are putting a strong VDD has to be more than 2 times the tau delay. Why should that be the case? Of course, if the triggering pulse is less than 2 times tau delay, if you apply for lesser than 2 times the tau delay, it is obvious that the regenerative power of the cross-coupled inverter can take over. So the regenerative power, for example, in this case, if we apply the pulse for less than 2 times of tau delay, by the time this strong input has passed through both these inverters and come back to facilitate the change, the inverters or the positive regenerative feedback will be able to overpower the signal. Therefore, this requirement of having the triggered pulse for more than 2 times the tau delay. So that is the one consideration. Now, having told you that this is the most viable way of overpowering the circuit, the positive feedback, to replace the value which was at N1 from 0 to 1, a question that I would want to ask you is, do you find something very, very contradictory that I am trying to prescribe over here compared to what we had seen in the read cycle? Let me repeat my question. There is something I am prescribing over here which is completely opposite to what I was suggesting in the read cycle. So take a moment to pause and think what that could be. So if you have been following this course very well, you will recognize that when we were doing the read cycle, the condition was that the pass gate transistor should be much weaker than the pull down transistor, which formed the heart of your cross couple inverter, right? That was the consideration when we were doing the read operation, and that was the cell ratio. Remember, the pass gate transistor strength should be lower compared to the pull down transistor. But now for write operation, we are suggesting exactly the opposite. We are suggesting to have an overpowering effect or in the write operation, the pass gate transistor needs to be very, very strong. Now, how do we reconcile these apparent conflicts between read and write? That is something that we will discuss a few classes from now. But I thought it is very important for us to note that read and write operations have often conflicting requirements. This is because read is supposed to be non-destructive, but write is supposed to be overpowering or destructive in the sense that you are trying to alter the values. Okay. Now, this is the technique of doing write operation, which is generally used in these SRAM cells. But this is not the only approach of trying to do a write operation. Another very interesting way of trying to do a write operation is trying to find out what is that force that you are trying to overpower. And the force that we are trying to overpower in trying to do the write operation is the positive regenerative feedback, right? It is the positive regenerative feedback. So a question can come to our mind. What if we just remove this positive regenerative feedback? And that can be done very intelligently. Remember, the source of the positive regenerative feedback was this feedback loop from the cross-coupled inverters. What if we can just place another transistor between the feedback loop, and when we want to do a write operation, we ensure that you isolate the feedback. You cut off the feedback loop. How do you cut off the feedback loop? How you just disable this enable signal. So if you disable this enable signal, when you turn it from 1 to 0, the feedback gets disconnected. If the feedback gets disconnected, they are simply two independent inverters. They don't have the positive feedback mechanism working anymore. So what you can do is you can disconnect the feedback and then alter this value. So you write from 0 to 1. Earlier you had a value of 0. You make it 1. And now you restore the feedback by putting the enable of this signal or the MOSFET which was connected to the feedback loop from 0 to 1. And after the feedback gets reconnected, your memory effect is restored again. Very interesting technique, but as you can understand, this will be a slightly complicated technique because now you're using another MOSFET to enable and disable the feedback loop. So it is a little bit larger overhead in terms of signals, in terms of routing, and also in terms of footprint. But the advantage in using this method is that you are no longer governed by this technique of the trigger pulse being more than 2 tau delay, and therefore it can give you faster writing speeds. And since it can give you much faster writing speeds, it is often used for registers in the ALU. As you know, as we have been studying, the registers in the arithmetic logic unit are working at much rapid speeds, and you need very fast access times with very low latency. So this kind of technique of writing could be very useful and is used for both MUX-based registers. So both these techniques are used to write into SRAM cells. But since we are focusing on SRAM cells for memory design, not really for MUX-based registers, we will focus on the first technique. The first technique was using an overpowering signal by having a very strong pass gate transistor. So with this in mind, let us start looking very carefully at our write operation. So in our write operation, what we have in front of us, we have the left branch, which is 0, and the intention is to flip it to 1, and our right branch has 1 and our intention is to flip it to 0. So the configuration we have is from the same as earlier where we were trying to read operation. So left branch had 0 and right branch had 1. In the read cycle, we just wanted to do a non-destructive read, but here we want to do a flipping of the bits. That means the left branch, storage node 1, will go from 0 to 1, and storage node 2 will go from 1 to 0. Okay, so that is the intention. So how do you do this? The first thing that you do is appropriately select the bit line and bit line bar. Now it should be common sense to us now. What should be the values of precharge that is put on bit line and bit line bar? Obviously, if I want to switch the storage node 1 from 0 to 1, the bit line should be, which is connected to the left hand side of the branch or the left hand side of the inverter as indicated in the diagram, has to be precharged to 1 and bit line bar has to be precharged to 0. Okay, so first step that we do is we precharge the bit line and bit line bar, and this is how we are deviating from the read operation. Remember, in the read operation, to do a non-destructive read, both the bit line and bit line bar will precharge to VDD or 1. Here, depending on what value you want to write into your left and right hand side of the branch, or to Q and Q bar or N1 and N2, you appropriately precharge the bit line and bit line bar, and this happens to be 1 and 0 in this particular case. Okay. Next, what do we do? Of course, having to turn on the pass gate transistor, we need to enable the word line. So the next important step is to turn on the word line. Okay, so let's take a moment to think about what will happen next. Where do you think, which branch will start reacting first or start responding first to this kind of biasing in bit line bar and word line? Take a moment to think about it. Okay, so if you have been following what we are saying for quite some time, you will first and foremost recognize that a very good way to do analysis in SRAM cells is to split the left and right hand side and analyze them separately. And if you do that, you will realize that the left hand side, which I am indicating from the laser pointer, is the biasing scheme, and the node voltages are exactly identical to the read operation. So the left hand side is very identical to the read operation, where the bit line is precharged to 1 and the word line has been asserted, and your internal storage node N1 is 0. Remember, we have selected the values of PG1 and PD1 such that the cell ratio is maintained, and under these conditions there will only be a small read current flowing from the bit line PG1 and PD1. So only thing that can happen under these conditions is a non-destructive read. Okay, so only non-destructive read is possible from the left hand side of the branch. So it is common sense that the left hand side of the branch will not contribute to the flipping of the bit. Okay, why is the left hand side will not contribute to the flipping of the bit? Because the left hand side of the branch is ensuring that there is only non-destructive read. So where will the bit flip start to occur from? Of course, it will start from the right hand side of the branch. So let us focus on the right hand side of the branch. So for our convenience, what I have essentially done is just redrawn the right hand side of the branch separately. First and foremost, we have to recognize that the input to the right hand side of the branch is node N1, which is 0 at the current moment. So if the input is 0 to the inverter, of course the pull down transistor will not be active, or the NMOS will not be active. What will be active is the pull up transistor and the pass gate transistor on the right hand side. Now, unlike the previous read operation, there will be a current that will flow now from the VDD through the pass gate transistor. Why is that the case? Because in read, bit line bar was precharged to 1, but now bit line bar, remember, is precharged to 0. So now let's do the analysis. What will be VGS? It will be VGS, which is the voltage. VG will be the voltage on the word line, and VS will be the voltage on the bit line bar. This VGS will be equal to VDD, and this is much greater than VTH. So the pass gate transistor will turn on. And because the pass gate transistor turns on, there will be a right current which will flow from VDD to the pull up transistor through the pass gate transistor into the bit line bar. Okay. Now the same analysis which we had done, we are going to repeat. Now remember, what was the objective in the read operation? The objective in read operation is that this internal node N1 or N2 in this case should not flip. So it should remain at 0. But now our objective is that in write operation is that the internal node N2 must flip. It must flip from 1 to 0. And as we know, if we do a similar analysis, if we want internal node N2 to flip from 1 to 0, the pass gate transistor has to be much stronger compared to the pull up transistor. And that is what I have indicated over here. So the pass gate transistor has to be stronger than the pull-up transistor, or in other words, the resistance or the on resistance of the pass gate transistor must be much lesser than the on resistance of the pull-up transistor. Now, unlike the previous case, there is no need to do transistor sizing anymore, because remember, pass gate transistor is NMOS and pull-up transistor is PMOS. Even if you have the same W by L ratio, remember, current was proportional to the mobility and W by L ratio. In silicon CMOS, since the mobility of electrons is much larger than holes, approximately 3 times larger than holes, it is easy to maintain that the on resistance of pass gate transistor is much lesser than the on resistance of the pull-up transistor with the same W by L ratio. And this ratio between the on resistance of the pull-up transistor divided by the on resistance of the pass gate transistor is now called the pull ratio. Remember, in read operation, the ratio between the pull down transistor and the pass gate transistor was called the cell ratio. Here it is called the pull ratio. Why is it called the pull ratio? Because you are trying to pull the value, or you are trying to flip the value from 1 to 0. Therefore, you try to ensure that the resistance of the pass gate transistor is much lesser than the resistance of the pull-up transistor. Okay, this is what forms the initiation phase of the write operation. So let us recall what we just looked at. In the phase 1 of your write operation, N1 had a value of 0 and N2 had a value of 1. Since the left hand side of the branch cannot contribute to a flipping or a destructive write, it can only contribute to a non-destructive read. We focus on the right hand side of the branch, and because in this case the pass gate transistor 2 has turned on, there is finite write current which flows through this branch from the pull-up, from VDD to the pull-up 2 transistor to pass gate 2 transistor, and as a result the value of 1 starts moving slowly to 1 minus V dash or towards 0. So this is the initial phase of, or the initiating phase of the write operation, right? Now what happens in the second phase? When the second phase of the write process is as follows. As the VN2 starts moving to a value of 0, remember that the VN2 is the input to the left hand side of the branch. Now the left hand side of the branch is connected to pull up 1 transistor and pull down 1 transistor. And since the value is flipping from 1 to 0, this will result in the switch off of pull down transistor 1 and a switch on of the pull up transistor 1, and as a result there will be a significant write current now appearing in the left hand side of the branch as well, which will flow from VDD to pull up 1 into storage node 1, and as this current flows, the storage node N1 will start getting charged from 0 to 1 volts, and as a result, after the flipping of storage node 2, there will be an eventual flipping of storage node 1 as well. So in a sense, while read operation was initiated from the branch which had storage node value of 0, the write operation is initiated from the branch where the storage node value was 1. So the storage node value 1 to 0 transition happens first, and then this results in the turning on of the pull up 1 transistor and the write current also charges the storage node N1 from 0 to 1. So this is in principle what was happening with the write operation. So let us conclude our discussion today. Next class we will look at the timing analysis of the write operation, followed by understanding of read and hold noise margins. Thank you.